Welcome friends, Igor is here, and in this video we will discover the vector form of solutions to linear systems and use it to show how null spaces can be used to construct solutions of non-homogeneous systems. In this lesson, we will develop a deeper understanding of the true role of free variables in describing infinite solution sets, prove that all solutions to a linear system can be obtained by taking one particular solution to that system and adding to that solution all possible vectors from the null space of the coefficient matrix, and discover that linear systems with singular coefficient matrices never have unique solutions. Let's get started. I will begin with an example that will illustrate the ideas we are going to develop today. We have a linear system with 3 equations and 4 variables. We know how to solve such a linear system. We construct the augmented matrix and we obtain the reduced row echelon form of the augmented matrix. From the reduced row echelon form, we see that x1 and x2 are the dependent variables and x3, x4 are the free variables, and we can write this infinite solution set by using 2 free variables. But now we are going to discover an alternative way to write the solution vector. I am going to use the operation of addition of vectors to split this vector into several individual vectors. In the first vector, I'm going to collect everything that does not involve a variable. In this case, it is a constant 4 in the first component, and there is nothing else in the other components. Well, that means these are simply zeros. Next, I'm going to collect everything that involves the free variable x3, and we obtain this column vector. Finally, I'm going to collect everything that involves the free variable x4, and we get this vector. You can easily check that if you add these 3 vectors, what you obtain is the original solution vector. Next, let's use the operation of scalar multiplication to factor out the free variable x3 from the second vector and the free variable x4 from the third vector. So we managed to express our solution vector in this alternative form using the operations of vector addition and scalar multiplication. Of course, we can still use this form to build infinitely many solutions to the original linear system by assigning specific values to the free variables x3 and x4. For example, if we assign a value of -1 to x3 and a value of 0 to x4, then we can compute a particular solution of the original linear system which corresponds to these values of the free variables. But this form of representing the solution vector tells us a lot more than that. If you really stare at this form long enough, you will see that every solution of the linear system looks as follows. It is one fixed vector 4, 0, 0, 0 plus some multiple of this second vector plus some multiple of the third vector. And the scalars that are used to multiply the last 2 vectors could be arbitrary because they correspond to free variables which are free to assume any values. This vector form of solution set tells us that in fact all we need to describe this whole infinite solution set is just 3 specific vectors. One of them is always used in its original fixed form. The other 2 can be scaled by arbitrary scalars. This gives us a deeper understanding of the role of free variables in describing infinite solution sets. Namely, they are used as scalars in linear combinations that produce the solution vectors. What we just saw in this example is the following phenomenon. To describe all possible solutions of the linear system, all we need is just one particular solution plus linear combinations of some vectors. What we're going to show now is that these vectors are not just arbitrary vectors. They are in fact solutions of the corresponding homogeneous linear system. In other words, they are vectors from the null space of the coefficient matrix. Suppose we have a linear system with A as the coefficient matrix and B as a vector of constants. Let W be one fixed particular solution of this linear system. Then a vector Y is a solution of this linear system if and only if Y is equal to the given fixed particular solution W plus some vector from the null space of the matrix A. Once again, we are being careful with proofs. We have an if and only if statement, and therefore there are two implications for us to prove. I recommend that before you start proving if and only if statements, you explicitly write the two implications that you need to establish. Let's denote by A1, A2 through AN the columns of the coefficient matrix A. In one direction, we are going to suppose that we have that fixed particular solution W, and we construct a vector Y by adding a vector from the null space of A to the given vector W. Our goal is to prove that this vector Y is also a solution to a linear system with A as the coefficient matrix and B as a vector of constants. I am going to start by constructing a linear combination of the columns of matrix A by using the components of the vector Y as scalars. We are given that the vector Y is equal to the vector W plus the vector Z. Therefore, each component of the vector Y is the corresponding component of the vector W plus the component of the vector Z. We already established some properties of vector operations. In particular, we proved that addition of scalars distributes to the addition of vectors via scalar multiplication. Also, we're using the property that addition of vectors is commutative to rearrange the terms. This long addition of vectors simplifies somewhat. Do you see why? This is because of our assumption that the vector Z comes from the null space of the matrix A. This means that the vector Z is a solution to the homogeneous linear system with A as the coefficient matrix and 0 as the vector of constants. Also, we already established that solutions to linear systems are linear combinations of the columns of the coefficient matrix that are equal to the vector of constants. So putting all these facts together, you see that the linear combination of the columns of the matrix A with the components of the vector Z as scalars is equal to the 0 vector. This is a consequence of our assumption that Z comes from the null space of the matrix A. We know that the 0 vector has a property that when you add this to another vector, you don't change anything, so it simply disappears from our expression. All that remains for us to do is to figure out what is the value of this linear combination, the linear combination of the columns of the matrix A with scalars being the components of the vector W. Do you see how this simplifies? This is equal to the vector B because of our assumption that W is a solution to the linear system with A as the coefficient matrix and B as a vector of constants. But now, if you look at the beginning and the end of this long list of equalities, you'll recognize that it means that vector Y is a solution to a linear system with A as the coefficient matrix and B as a vector of constants. This is exactly what we were trying to prove in this implication. In the other direction, we are going to assume that we take any solution of the linear system with A as the coefficient matrix and B as a vector of constants. Let's say that this solution is the vector Y. What we need to prove is that this vector Y can be represented as our fixed particular solution W plus something from the null space of the matrix A. At this point, you may tell yourself, how the hell am I supposed to figure out this? But let's not despair. Let's be methodical, logical, and creative. Let's think in following terms. What's given to us, what we cannot change, and what we are free to construct, what we are free to choose. When you think in these terms, it should be clear that the vector y is given to you. You chose some solution of the linear system. Also, the vector w was fixed at the very beginning of the assumption of the theorem, and therefore, the only freedom of choice you have in this equation is the vector z. Do you see what you need to do now? You're simply looking for a vector z that satisfies the equation vector y is equal to vector w plus vector z. But I hope you see now that the only chance for this equation to work out is for the vector z to be equal to y minus w. So, are we done with the proof if we simply say let vector z be equal to y minus w, because then the equation we're trying to prove is obviously going to be satisfied? Well, not quite, because we need to find not just any vector z. This vector z must come from the null space of the matrix A. And therefore, what's left for us to prove is that the vector y minus w belongs to the null space of the matrix A, and this is what we'll embark to do now. I hope this explanation helps you to see the thinking process behind constructing these proofs. When you see a proof in the textbook, it is already shown in its final polished form, but this is not the way this proof is usually initially constructed. So if I simply started with this expression, then you would wonder, why do you even look at this? But now I hope you see what kind of preparation went into realizing that this is what we need to do. So we form a linear combination of the columns of the matrix A, and we use components of the vector y minus w as scalars. You may ask, well, what is the vector y minus w, because we have not defined the operation of subtraction of vectors. We only defined the operation of addition of vectors. Think about this as follows. To subtract a vector means to add its additive inverse. So vector y minus vector w is the same as vector y plus the negative of vector w. Now you see that each component of this vector is simply the corresponding component of vector y minus the component of vector w. Next, we use the distributive property of vector operations and the fact that vector addition is a commutative operation. All of this simplifies to simply vector b minus vector b. Do you see why? The first linear combination is equal to the vector b because we assumed that y is a solution to a linear system with A as the coefficient matrix and b as a vector of constants. And the second linear combination is equal to the vector b because we pre-assumed in the theorem that w is a solution to this same linear system. But now vector b minus vector b is equal to the zero vector. And if you see at the beginning and the end of this long expression, you will realize it says that vector y minus w is a solution to a homogeneous linear system with A as the coefficient matrix. But the solutions to homogeneous linear systems are precisely the elements of the null space of the coefficient matrix. So in essence, this says that vector y minus w is an element of the null space of the matrix A. In other words, vector y minus vector w is equal to some vector z from the null space of A. Now, if you rewrite this, it simply says vector y is equal to the vector w plus some vector z from the null space of the matrix A, and this is exactly what we were trying to prove. Let me summarize. Essentially, we constructed the vector z as y minus w, and we had to show that this vector belongs to the null space of the matrix A. Moreover, this construction is the only possible value for vector z, because if y is equal to w plus z, then z must be equal to y minus w. This was the entire reasoning behind this proof. Now is the time to be fair and equitable. we devoted quite a bit of attention to non-singular matrices, and in particular we proved that if you have a linear system with a non-singular coefficient matrix, then this linear system always has a unique solution no matter what the vector of constants is. Yet, we do not know what happens for singular matrices. We have not yet discussed it. So, here is a question. If you have a linear system whose coefficient matrix is a singular matrix, what can you say about the solution set of such a linear system? Well, first of all, if the linear system is inconsistent, then it means there are no solutions. Here's the question. Is it possible for a linear system with a singular coefficient matrix to be inconsistent? Please construct an example of a linear system with singular coefficient matrix which is inconsistent, which has no solutions. Write this example in the comments down below, and I will do my best to respond to every comment. The complementary case is when the linear system is consistent. It means there is at least one solution. So let's choose one such solution W. By what we just proved, all solutions to this linear system can be obtained by taking this one particular solution W and adding all the possible elements from the null space of the coefficient matrix A. But we know that the null space of a singular matrix is infinite, because a singular matrix is characterized as a square matrix for which the homogeneous linear system has infinitely many solutions. In turn, this means that the solution set of the linear system, the original possibly non-homogeneous linear system, is infinite, because you can take one particular solution W and add infinitely many vectors from the null space of A. What this argument shows is that if you have a linear system with a singular coefficient matrix, then this linear system never has a unique solution. It may have no solutions or infinitely many solutions, but not a unique solution. In this sense, non-singular and singular matrices are polar opposites of each other. Non-singular matrices result in linear systems with unique solutions, while singular matrices result in linear systems which never have unique solutions. If you found this video useful, please like it to help others discover this content, and subscribe to this channel to see future videos. In the next video in this series, we will consider spans of column vectors. I will see you later.